Thank you for the introduction. As mentioned, I'm Žiga Žnidarič from the Faculty of Engineering of the University of Maribor, and I will be going over basically what was my master's thesis, where I analyzed these two cellular structures, which you can see on the screens now, both being engineered on the faculty, the left one being the original structure and the right being an optimized version for better energy absorption. I will be going over how we basically modeled these two structures, how we prepare them for the analysis, and then at the end present the results and compare them between these two. So modeling these structures, we didn't use the entire geometry. We only used basically one slice of the entire cylinder because they were symmetric. So we modified a Python script that was made to only give us this basically one row of unit cells with these struts to connect them to the neighboring cells. We then used some linear patterns and mirroring to create this large sort of tall structure, wireframe structure, that is comprised out of 11 cells vertically and 3 struts horizontally. We then made this Y structure into a volumetric model. All of the struts are a cylindrical shape, with the original structure, the left one, having a diameter of 0.43 millimeters, and with the optimized one ranging from 0.1 to 0.9 millimeters in diameter. Then we had to clean the models a bit up with these planes that we created. The vertical planes were used to basically create 1/14 of the entire structure. And so we have nice planes on which we will later put the boundary conditions and loads. And the horizontal planes were used to basically give us a place to put the loads. So we end up with a structure that is 9 unit cells tall and 2 unit cells wide, or 1/14 of the entire geometry. The material that was used was 316Al stainless steel, which is a common material when creating these sorts of complex cellular structures made with additive manufacturing. The first table shows the strain life parameters that we used, and in the second table we see the parameters used for modeling the elastic and the plastic response. Instead of using basically data points in a table to model the plastic response, we use the Chebosh kinematic hardening, which uses basically an equation in the background with these parameters to model its plastic response. Then the loads, we loaded both structures with displacement and with 3 different shapes. The first was alternating, where the load went, or the displacement went into tension and then into compression. In the second case, it only went into compression, and lastly, only into tension. And the loads were put on the faces that were previously cut with the horizontal planes. And the rest of the boundary conditions on all of these faces, we put frictionless supports. Ideally, we would have used some sort of symmetry, but the program that we used didn't allow it. So we had to do with these types of supports. These basically don't allow any movement perpendicular to the face that they were assigned to. So in the right picture, none of these faces can move in or out of the screen. They can move in the Z direction and X direction. And similarly, and the same boundary condition was put on all of these faces except this one. That is because if we put the same boundary condition on this one, the model would be underdefined. So we just had it fixed in place. We also did the convergence analysis to get the idea of what kind of finite element size we should use, and we chose 0.1 millimeters. We used a hex-dominated mesh with the quadratic interpolation on the original model, and on the optimized model, we had to modify it somewhat. The thinnest struts use the smaller elements, and the biggest used 0.15 element size, just because if we didn't do that, the model either didn't mesh or it would be too large to even simulate. We were careful that the number of elements through the cross-section would be at least as much as in the original structure. And then for fatigue life, we use the strain life method with the Morrow model, and all of the stresses that we use in the calculation were von Mises principal stresses. The results, the least amount of cycles that will be gotten when the structures are loaded with the alternating load. So first into tension and then into compression. And the most number of cycles will be had when the structures are loaded only under compression, which is to be expected because that's what they were basically designed to do. Contrary to what we thought would happen, the optimized structure had a shorter lifespan in all cases. And we also made the trend lines and had the equations written out, and we can see that the exponent that gives us how much the slope of the trend line shows that in each case the optimized structure has a greater slope, which I'll comment in the conclusions. We also analyzed the stresses. We can see that the maximum stresses were achieved basically at the peaks of the sine waves in both cases, just in the original structure in the innermost unit cell and the optimized in the outermost. What's nice is that we didn't get any concentration of stresses in these parts where we would expect because of the sharp edges and similar. The same could be said for plastic strains. They were in the same spots as the stresses. And here we have a model that's representative on which we can see why we call this structure optimized is because of the stress that is throughout the structure. In the original geometry, we can see the outermost cells are the least, have the least amount of stress, while the innermost are the most stress, whereas these have a more, is better distributed through the entire structure, which gives us which has the consequence in which is what we believe is the reason why we have a shorter life, is that it gives it a higher stiffness and higher energy absorption. One of the reasons could also be the higher amounts of plastic strains. And one point that I would like to make, or something that we could research further, is with the trend lines, because the slopes of the trend lines are steeper in the optimized structure, there could be a case where at higher strains or larger strains, the optimized structure would actually have a longer life expectancy than the original one. And on that, I would like to finish my presentation.